Welcome to this YouTube tutorial series on implementing templates and generics in C. Before we begin, I'm going to start off with some prerequisites. I'm going to assume you guys have knowledge of data structures, knowledge of templates and generics in general, knowledge of actually programming in C, and knowledge of good memory management skills, such as using malloc and free, etc. Before we begin, I'm going to give a quick review. So, in programs, memory is stored in contiguous adjacent blocks and cells, where contiguous simply means adjacent. So imagine a gigantic array of memory where each slot or each entry in our array is a block or a cell. And these cells can be combined into blocks that allow for data structures to be stored into. Memory is laid out into different sections. The most notably, we have the stack and the heap. The stack is where temporary variables such as function variables are stored, and they are destroyed when the end of the function scope has been reached, such as when the function returns. So let's say we have a simple function that just calculates some data. Any temporary variables that we declare and initialize in that function, it is stored on the stack, and whenever we return a value, that memory on the stack is then destroyed and released. And if you guys probably know, there's a famous website called Stack Overflow, and this is actually an error that occurs usually when an infinite loop is declaring new variables. And so the stack has limited memory. On the contrast, we have the heap, which is where dynamic memory is allocated, and this memory stays allocated until freed or until the end of the program. The heap is more useful simply because the memory stays there until the end of the program or until you want to actually release it. On contrast, the stack, the memory is released and destroyed whenever the scope of the function has gone out of its reach. The heap has more memory availability than the stack, but forgetting to free allocated memory when done will actually cause memory leaks. A pointer, so now since we're done talking about memory, let's move on to pointers. A pointer is simply a group of cells that hold an address. Pointers are very common and necessary in C for a number of reasons. One example is that C passes arguments to functions by value. So if you actually want to change the value of a variable passed in, you have to change the variable at that memory address by use of a pointer. Pointers can be of any type: character, integer, double, float, or even user-defined values such as structs. But these pointers can only point to their respective types. Once you declare a variable to point to a double, it can only point to a double. It can no longer point to an integer or a float. So as a quick review of templates and generics, let's go over this. Even though there are many differences between Java's generics and C++'s templates, they both share the overarching theme: code reusability. They allow functions and classes to be extended and reused for different types. So now I'm going to give two small examples of a template in C and a generic in Java. Note, the T symbol denotes the type of data being used. It can either be a user-defined type or a primitive type. So we're going to define a class in both C++ and Java that simply creates an array with two basic functions: set an entry and get an entry. So in C++, we declare a template by usage of the template keyword, and we denote the data type being used as T. So now whenever we create our class myArray as an instance or an object, we pass in whatever data type we want to, and it is referenced to by T. So now we create an array of type T here as a private variable, and then we have our set entry and our get entry. Our get entry returns a T value, and our set entry requires a T value parameter. And so this is how you actually create a basic template in C++. In Java, we have generics. And so here in Java, you denote a generic not by a generic keyword, but actually by angled brackets. So here we can have multiple arguments for generics, but in this instance, I'm going to just pertain to one. So here we have T, and whenever we would call this function, call this class, we would say myArray angled bracket our data type, and then we would have a new. We would call new myArray and initialize that data. And so it's the same methods the same sort of flow but different syntax. The most common usage for templates and generics is for creating data structures provided in the standard template library of Java and C++. So using a vector, using a list, a linked list, a hash map, using some kind of tree, and all these data structures are either templates or generics in their respective languages. They simply allow you to use the same code just for different data types. So the ability of being able to store different classes, structures, and primitive data inside templated data structures allow for the same code to not be repeated for different data types. However, in C, there is no availability of templates or generics, neither a standard template library of data structures. So in C, if you want to store your own data, you have to create data structures, which can be a very painful process, especially if you're having to recreate the same data structures for different data, such as one for some kind of pointer to a double, or a structure, or a pointer to a structure which contains a structure. So how do we create templates for classes or functions? And this should not be classes, this should be structs or functions in C without rewriting the same data structures in each project, but with different types? The answer is with void pointers. In C, a void pointer, denoted by void star, is known as a generic pointer. It can point to any type. It simply points to the beginning of a memory block. And so one of the big warnings of void pointers is that they cannot be dereferenced. So in C, here's a quick example. We declare an integer pointer, a, we point to the value 5, then we declare a void pointer, b, which then points to a. If we want to get the value of b and then store that into an integer pointer c, we cannot do this because it would simply raise an error. We must first cast the void pointer back into its original type before we can dereference it. So because void pointer can be any type, they can be casted to incorrect data types. So here we have a small little picture of a contiguous block of memory. We have 4 bytes allocated to some kind of integer value. We have 6 bytes that have been uninitialized. We have 12 bytes allocated to a user-defined struct, and 4 more bytes allocated to an integer. So let's say, for example, we have our void pointer a, which points here. Okay, and then let's say we want to actually cast our void pointer, which should be an integer, to some struct, let's say of size 12 bytes. So if we were to cast this void pointer, which starts here, it would take up 12 bytes, which would actually run over this uninitialized value and into this initialized value. So now when we access that structure that we just casted from our void pointer, we're getting memory that has not been initialized, we're getting memory that has been initialized for other structs, and it creates a big problem, and it will actually cause your memory to segfault. So this is a big warning that casting void pointers to the incorrect type from which it originally was will cause major errors in your program. However, the strength is that we can actually create structures and functions that accept void pointers, where void pointer is simply a wildcard. It can be any kind of structure or value we place in it. Therefore, we can allow the same code to be reused but with different data types. And here's a quick example. When allocating new memory using malloc, it actually returns void pointer. This is why we actually cast malloc. So it is, you don't have to necessarily cast, it will still run. However, it is good procedure to cast our mallocs to show good programming. And one last thing I'm going to talk about is pointer functions. In C, it is possible to have pointers to functions, and this allows them to actually be passed as parameters, placed in arrays, and returned from functions. Function pointers do not point to memory, but to code. Function pointers are very common with generic data structures in C, and so it is good to be familiar with them, and I will eventually go over them in later videos. For example, in the standard template library of C, there exists a generic function called qsort that is able to sort any type of data given a comparator function. This comparator function must be a user-defined function and must be passed as a pointer to the qsort function. So we pass this pointer to a function to qsort, and whenever qsort needs to compare two data structures or two data types, it will actually go back to our pointed to function and then call that function. So this is a very powerful thing, and I will eventually get into these pointer functions. Before we end this video, there's two things I forgot to check. Here on line 86, when we cast our void pointer back into an int pointer, we do not want to dereference that value. This is going to cause a cast type error. And secondly, I can't even believe I've done this, but whenever you never want to directly assign an integer pointer to a primitive type, because the purpose of a pointer is to hold the address of a variable or a value. Whenever you directly assign a pointer to a primitive type, you're just assigning it a value instead of an address. So this is going to cause an error. So to fix this, you would say integer temp is equal to 5, and now we're going to point to the address of temp. And then when we dereference int, so let's say printf %d, we would dereference a, and then we would get the value at the address of temp, which is 5. So this is a little bit of a mistake I forgot to check over. But in the next video, we're actually going to introduce void pointers in actual code. So today, I just wanted to go over the basic introduction, and in the next video, we'll go more in depth over this topic. So stay tuned.